On average, like what do kids usually get on their midterm?
I don't know. So this is the first time I teach in this format, which I teach the whole thing twice. So we'll see. But I expect the midterm to be a lot easier than the final, so you better get 100%. Any other question? All right, let's get started. So you probably have seen this in your lab yesterday. This is how a wave will be reflected by a fixed end. As you can see, as it bounces onto the fixed end, Newton's third law just apply opposite direction of force and make it go in the opposite direction. But if you have a loose end, then the inertia of the wave will make the wave go back in the same direction. So for a fixed end, you will have this reverse when you reflect the wave back. And for a free end, now this is a fixed end. So you see it hit the wall and the wall hit back, so it get flipped to the opposite direction. And for a free end, the end is loose, so it just go up, and then as it goes down back, it creates the wave that have the same direction, same orientation as the incident wave. So the incident wave is going right, and the reflected wave is also going to your right. This is the reflection of wave when you encounter two different type of boundary conditions. And if the wave go from a faster medium to a slower medium, even though the stinky here looks thicker, but it is lighter, so it will make the wave travel faster. When it goes from faster to slower, the slower end is like a hard fixed end, so it's like hitting a hard wall, and it just reflects the wave into the opposite orientation. Let's watch it again. And pay attention to the transmitted wave. The transmitted wave is in the same orientation as the incident wave. So that is the reflection of wave. If you instead entering a slower median, you get a faster median, then it's like hitting a free end. Any questions so far? Okay, so that's the reflection of wave. Now take out your eye clicker. What of the transmitted wave must be the same as the incident wave? So if I have an incident wave with some wavelength, wave speed, and frequency, which one must be the same for the transmitted wave, the wave that enters the new median? So I will set it for 1 minute so that we don't waste your time and you know when to respond. This is only counted by participation, so don't worry if you get the wrong answer. You have a wave going here, and you have a wave, you hit a median, in the median shake. What will be the same for the incident wave and the transmitted wave? Okay, so let's say this is the new median. A wave has a frequency, so the incident wave will hit the new median with a frequency. Every time the incident wave hit the median, the transmitted wave got generated in the new median. So if an incident wave hit the median 2 times per second, then in the new median, there will be the new wave will be generated 2 times per second. So the frequency of the incident wave hitting the median will be the same as the frequency of the transmitted wave. So the frequency will always be the same. Okay? The wavelength may be different, and that's why the speed may be different. in two medium, the wave travels in different speed, but the frequency of them must be the same because they came from the same heating. Okay. Now, there's a cool thing that will happen when you have two periodic waves traveling against each other. What you will see is something called a standing wave. You will see why it's called a standing wave in a short time. So these two people are generating periodic wave, and the waves are going into each other. So now you see after the wave get added together by superposition, the resulting wave doesn't move toward the top and it doesn't move toward the bottom. It just stands there. The Hsing-Yi or the string is wiggling, but the wave is not going anywhere. It is standing right there. That's why we call it a standing wave. And for a standing wave, you will see that there are some points that just doesn't move away from the equilibrium position. Those points that after you add two waves just doesn't move, which the wave always cancel each other, is called the knots. They are having destructive interference. The two waves just always destroy each other and always cancel each other at these points. So these points are called the knots. And for the points that the wave becomes really big, the two waves that form this standing wave are always having constructive interference at these points. These points are called anti-knot. They will move so the wave will have the maximum amplitude at this anti-knot because the two wave forming them is always having constructive interference. Now, this is a one-dimensional case. You do see something similar when you look at two-dimensional wave having interference. So you see there are some blurry lines that the water just doesn't move. Along these lines are actually a bunch of knots that the wave from the two sources always cancel each other. So along these blurry lines, which the water just doesn't move, are actually lines formed by tons of knots. And the thing in between are the anti-knots. So you see on two dimensions, it's actually easier to recognize the knots, which the wave is just zero. The anti-knot is not that outstanding compared to its surrounding. And the connection between the one dimension and two dimension is that if you only focus on the water surface across this line, you will see that on this line, this point is a knot, that point is a knot, a knot, a knot. So at the end, along this line, the water surface is vibrating, is oscillating like this, which you can recognize is a one-dimensional standing wave. Yeah?
Does the correlation between energy, amplitude, and radius change between one-dimensional and two-dimensional?
So the energy is always proportional to amplitude squared because it cannot be negative. The coefficient in the front might change from like the linear mass density to the surface density or something else, but the tendency to the amplitude is always proportional to amplitude squared. Good. Any other question? Good. So another thing about energy is that we know a wave will transmit energy. Energy is the thing that the wave is actually transporting. The wave doesn't transport matter, it transports energy. But when you have a standing wave, energy is localized at the anti-knot. The knots carry no energy because it's never moving. So a standing wave is like a way to organize the energy and distribute them at some point localized around the anti-knot. Energy is still conserved. It's just that they got distributed at different locations. So this is the wave itself. It can go up and down, positive, negative. But if you look at the intensity, it should always be positive because intensity is amplitude squared. then you will have this kind of diagram which shows that at the node, the intensity of the wave is 0, and at the anti-node, you will see a peak of intensity. And you will see this kind of pattern later. But so far, that is standing wave. Any more question with standing wave? Okay. Now, the last thing we want to look at for just wave in general is what will happen when a wave hits a barrier, when it hits some obstacle. So here's a water wave generated by some machine. You can try to block it with some plates. And what you see is that when a wave encounters an obstacle, it can actually go around the obstacle. It can go around the barrier. This is called the diffraction of wave. This is very different than particle. If you have particle going through the slit, it just hits somewhere behind the opening. But the wave can go around the opening and reach somewhere that is behind the barrier. When you have different size of opening, you have different amount of diffraction. What you see here is that when you have a big opening, the wave kind of spread out a little bit, but it doesn't go all the way out across the 180-degree angle. But here, when you have a very small, narrow opening, the wave pretty much go out for the entire 180-degree angle. So you see that when you have a narrower opening, it is more obvious that the wave has this diffraction tendency. So you see when the opening is smaller, there will be more diffraction of the wave. Any question? So this is important. When the opening is small, there's actually more diffraction. Instead of big opening, big diffraction. You have small opening, big diffraction. Now, how about the wave? Yeah, any question?
Wait, so the reason that it's 20, like, completely goes out is because of more diffraction. Could you just repeat that again? Just explain why on the narrow one it goes all the way out.
I haven't explained why.
Oh,
so it's
sorry.
Okay if you don't understand why yet. Right now, it's just an experimental observation that if you have a smaller opening, you have more diffraction. Any other question? All right, so this is the opening itself. Let's try to look at the property of wave. Here you have a opening, or you have two openings with the same size, but on your left-hand side, the wavelength of the wave is longer, and on your right-hand side, the wavelength of the wave is shorter. You see that when you have a short wavelength, the diffraction is not that obvious. And if you have a long wavelength, the wave can easily go around the obstacle and have a significant amount of diffraction. So longer wavelength, smaller opening, wider spread of diffraction pattern. Okay? So we see if you have a long wavelength, there's also more diffraction. Now, we can understand this phenomenon using something called the Huygens principle. This principle will be used after diffraction, but it's good to explain diffraction, so that's why I'm still mentioning it. The Huygens principle is that when a wave is propagating, you see the lines formed by the water wave. We imagine that the line consists of a lot of point sources, each creating this circular wave. So when you look at a wavefront, the way that the wave propagates is by creating a circular wave on every single point source. And then the resulting wavefront will, of course, be the combination of all of them. On this wavefront, there are infinite amount of point sources. So when you draw all the circular wave that the point source created, all those point sources together will create a straight wavefront, and that's how the wave propagates. So you see the wave is at here right now, and you want to figure out how will the wave propagate, you draw a circle on every point of the current wavefront and combine the circle together. If you draw enough points, you should get the correct new wavefront. How does that explain diffraction? When you touch a barrier, the wavefront at the edge of the barrier creates a circular wavefront, and there's no other wave sources down here to create more wavefronts so that it doesn't form a straight line by the curve. So that's why the wave can spread out like this when you encounter a barrier. So that's Huygens principle. Okay? And there's no more calculation you need to do with this principle. That's just a qualitative explanation. Any question? So this is diffraction. A wave will go around the obstacle. This is a different property compared with a particle, yeah?
Does this explain why the longer wavelength goes around the barriers easier?
Good question. It doesn't. It's not obvious. So for that, you can do some calculation as we will see later. Any other question? Good. So those are the general introduction of wave. The next example of wave is what we call electromagnetic wave, which is light. So the light you see coming from all these light bulbs and the projector are waves. They are the propagation, or they are the disturbance of electric and magnetic field in the air or in the vacuum or whatever you are living in. Now, you cannot see electric and magnetic field, but we can draw it. They are vectors. They have directions. Just because I draw it like this doesn't mean the electric field goes up and down. This picture corresponds to this. Okay, so this is a electromagnetic wave. Electric field go up, and magnetic field go here, and then electric field go down, magnetic field go here. When light propagates in this direction, the electric field at this point will go up, down. Okay, it goes down, up, down. And the magnetic field goes left, right. Just because I draw it like this doesn't mean the electric field must go up and down, because you can rotate it. You can also have a light that the electric field is going left and right, but magnetic field goes up and down. The electric and magnetic field can go in any direction as long as the relative direction is satisfied. The rule is that the electric field cross magnetic field will be the direction that the wave is propagating, which I call k hat. So if you look at this thing, right now, if you know, so right-hand rule. Let's make sure you know how to do right-hand rule. It is important, not in this class, but in 9C. Electric field, cross magnetic field, then the sum will be the direction that the wave is traveling. You can use the other part. You see, even though when electric field is going down, magnetic field now goes this way, so the right-hand rule still gives you the same direction. You can rotate your E and M wave and right-hand rule. E plus B, your sum points toward the direction that the wave is propagating. Okay? Now, this arrow just tells you the direction that the light is traveling. But if you want to describe the difference between this light and the light that the electric field goes sideways, we call these two different polarization. Usually we focus on the electric field. We say this is vertically polarized and this is horizontally polarized. Okay? Yeah.
Which property determines like it's vertical or horizontally polarized? Is it electric field or the magnetic field?
So we usually focus on electric field because magnetic field doesn't really do anything, even though you haven't done 9C yet. So I have to just tell you that. You don't need to know why this is true, but you do need to know this common sense that electric field, magnetic field, wave travels this way. Any other question? All right, so now pass this around. Make sure you know E equals B is the direction that the wave travels. pass this around. Now, make sure you understand it, because now I'm going to question you which one is actually a physical electromagnetic wave. They cannot go, the electric field and magnetic field cannot go up. It is not arbitrary for the direction of electric magnetic field. They must follow some physical rule, which the direction of E cross direction of B need to be the direction that the wave is traveling. If you're holding the electromagnetic field, you better get this answer correct. Just use your right hand rule. Do your right hand rule and see which one gives you the, to see which electromagnetic wave follows the right hand rule. Only the one that follows the right hand rule is a one that can actually show up in our universe. $20 seconds. So here, do your right hand rule. E cross B go up. Indeed, the wave is going that way. For this one, if you do E cross B, the wave should go in the opposite direction. So this one is wrong. This is not an electromagnetic wave. This is something else. It cannot be an electromagnetic wave. Good, good. Not so bad. Not so bad. So this is the correct one. Any question? Yeah. So this is electric field going up, magnetic field points toward you, out of the screen. So I have to curve my finger toward the B field, which is this way, not this way. So then my thumb will go backward. Good. So if you do a lower set, you'll see now E goes down and B goes into the screen. So if you do a right hand rule on the lower side, E cross B still give you the same result. Good. Any other question? Right hand rule, very important. Yeah. So these two, first of all, there's only one electromagnetic wave, but if you draw this to this direction, so let's say this one is the right one and the K is in this direction now, then they have different polarization because one has electric field going up and down and one has electric field going horizontally. So for these two, the polarization is perpendicular. Any other question? Yeah? Okay, so use your finger toward the first vector and curve it toward the second arrow. Then your thumb will be the resulting cross product. The reason why I curve up, not down, is because B is going up. So first A, and then curl to B, then your thumb will be A cross B. Okay? Any other question? Okay, good. So light is a wave. A wave has wavelengths. The electromagnetic wave you are looking at right now, the visible light, has wavelengths between 800 to 400 nanometer, approximately. I'm not the authority to determine this number, but this range is it's easy to remember. And I expect you to notice this is common sense for STEM major. And it is also common sense that the red light have longer wavelengths and the blue light have shorter wavelengths. If you go even shorter, it becomes invisible for a human eye, but the electromagnetic wave is still there. They are called UV ray, X-ray, gamma ray. So you see, the shorter the wavelength, the more dangerous the light is. If you go longer wavelengths, it again becomes invisible because your eyeball just doesn't detect it anymore, but the wave is still there. You can feel them by heat. The radiation from the campfire and your heater are longer than visible light, but you can feel the heat from it. And if you go longer, it's microwave and some other radio stuff. So your phone emits this wavelength. What kills you is this wavelength. Is using your phone dangerous? No, good. So don't worry about using your phone too much.
The sun is more dangerous.
What?
The sun is more dangerous.
Well, the sun has all of them. Not just visible light, it also has UV and infrared. Yeah. Any other question? So to compare with it, the sound wave have typical wavelengths like meter, 2 meter, 10 meter. It is longer than light. We just learned that for diffraction, you need to have longer wavelength to go around barrier. So it is very easy for sound wave to go around those doors, and the people outside there can hear what we are saying, but they cannot see the projector because light wave is not long enough to go around the barrier by diffraction. Okay? All right, so there are 3 phenomena that we need to discuss today. They are all diffraction or interference. One is called single slit, which you pass through a laser through a vertical slit. Note that the slit is vertical, but what you will see is that the pattern becomes horizontal, it's spread out. Because we say the narrower the opening is, the more significant the diffraction. So if you have a narrow width, the wave will spread out by diffraction, and you see this widespread pattern horizontally. If you have 2, you will see something like this. And if you have many, which we call diffraction grating, you will see that the energy got concentrated at sharp peaks. So this is just a projector. We have real thing over here. Let's see if I can turn it on. Let's try the single slit first. It's over here. So this is single slit. You see a single, no, is that a single slit? Give me a sec. But yeah, that's a single slit. You see, the slit is very small, and when you get over here, the center becomes pretty wide because of diffraction. There are something more at the side, which I will explain later, but you see, I'm not lying to you. This is how the diffraction pattern looks like for a single slit. And now for the double slit, so for a double slit, you see the center one is equally wide as the side one. For a single slit, the center one will be twice as wide, but here the center light spot is the same as the other light spot, is equally wide. Yeah?
Are the places where like there's no light other than nodes?
Yeah, so those dark fringes will correspond to the nodes created by the interference of 2 light waves. I will get to that later. Now for diffraction grating, you will see that the light wave is concentrated at some sharp point. See? Compared to just double slit, when you add a lot of slits, what you'll end up seeing is that the energy got super concentrated at this point. Diffraction grating has this kind of property, which it concentrates light. It's pretty useful in experiment, but I don't do experiments, so I cannot tell you more. All right, any questions so far? We can waste energy. I don't have to turn it off. Okay, so let's start from the single slit. we say when you have a wave that passes through a slit, so it's actually, you will have diffraction, which the wave spread out. That is what happens for a single slit. This center white spot here is the spread out caused by diffraction. Laser is light, light is wave. When the laser hit a small opening, the wave go around the opening and create this center spot. Okay? Yeah? Yeah, it's on Canvas, same with the first one. And also there will be lecture recording. Any other question? All right, make sure you don't have question because now I'm going to question you. Based on what we learned about diffraction, which one should correspond to a wider single slit? Which pattern should be created by a wider opening? Thirty seconds. Okay, let's review the answer. We want wider slit. The bottom one is 0.36 and the top one is 0.19. The bottom one is caused by a wider slit. So let's review why this should be true. For wave passing through a barrier, when you have a wider slit, what you see is that the wave doesn't spread out as much compared to a narrow slit. Same for this laser and single slit diffraction. When the laser passes through a narrower opening, when the slit is smaller, it actually causes more diffraction and causes the wave to spread out more. So when you look at the diffraction pattern on the wall, you will see a wider bright spot at the center. So that's why a narrower single slit will cause a wider spot at the center, and a wider slit will actually cause a narrower spot. That's how wave behaves. Make sure you know that because that's going to be on a tendency check on your homework. That's the hint. For diffraction, the wider the slit, the smaller the spot of the pattern. Any question? Yeah.
How do you think that as like the wider the slit, the more energy is concentrated?
You can say that. Yeah. Any other question? Okay. Yeah.
So like if you were to graph out the wave when you like put that into if you do a state machine forever, if you graph that, would it be like some sort of depression harmonic or something? Like
So if you look at a wave, so I will show you later, but a quick peek is that this is what happens when you have double slit interference. This two wave source is a two slit, and the electromagnetic wave is actually three-dimensional. If you look at the slit, which is pretty much long in this direction, and it's pretty much the same along the top and bottom, so you can approximate as two-dimensional. So the electromagnetic wave here is actually a two-dimensional thing that spread out and hit the screen later. So this is the complete wave pattern, just this part. You will see this thing later, okay? Any other question? Yeah? Yes. This is a problem with too many animation. Yeah. It's wider. Oh, you mean the pattern? Good. So let's look at not electromagnetic wave, but water wave. Oh, so you see the bright spot is okay. Maybe you think this is the whole thing. Is that the reason? Or okay, by choice. This is too blurry, but there should be like dark fringes over here. Okay, so you can compare the outer spot. You can see the outer spot is shorter compared to the upper one. Okay, any other question? All right. So now let's look at double slit interference. I hope you have done your homework so you know when you have two point source and the wave starts traveling, they can create different type of interference when they hit different spots. When you look at the point on the screen that is right at the center, this point should be equally far away from the two slits. When the laser hits the slit, it creates two wave sources, and the two wave sources travel to a point on the screen with no path difference. In this case, they either both go up or go down, and they will help each other form constructed interference, and you will see a bright spot at the center. As you move to the right of the screen, you're looking at a point that is closer to the right slit, but far away from the left slit. If you move far enough, you will hit a point which is half wavelength closer to the right slit, and that will cause the two waves to cancel each other by disrupting interference. So that's why when you move away from the center, you will hit a dark fringe or a knot, which looks black on the screen. But as you get further away to the right, you get even closer to the right fringe, right slit, and further from the left slit, such that now the path difference between the point and the two openings is a single wavelength. When you have a single wavelength of path difference, the one that travels a longer distance will go down and up again. So when they hit the screen, they still end up helping each other, and that's a constructed interference. So from the center to the side, you will see a bright spot, and then the intensity slowly decreases to a dark fringe, and then it will increase again. And that's why you see this pattern, which at the center, you have constructive and then destructive. And then when you go to one wavelength, it becomes constructive again. And then you get 3/2 wavelengths that's destructive, constructive, destructive. Same with the other side. So that's why you see this double slit interference pattern. Any question? So some terminology. The one at the center is usually called the zeroth bright fringe, or the center bright fringe. And then we call the next one the first bright fringe, the second bright fringe, and third, fourth, etc., etc. For the dark one, this is the first dark fringe. There's no zeros. There's just first dark fringe, and then second dark fringe, first, second, third, fourth. I am too lazy to put all the animation, but that's the terminology. Okay? Any question? Yeah?
So it's the same thing on both sides, right? Like first dark fringe is on both sides.
Yes, it's symmetric. In the formula, you might see 1 minus 1, 2 minus 2, but you know what I mean. Any other question? Yeah?
So there's no zeros.
What? Oh yeah, I don't think there's a zero stop fringe because then, so for bright fringe, you can label these two as 1 and -1. And for the zeros one, it's right at the center, so +0, -0 is the same. And here, the dark fringe is different, left and right, so this is 1, -1, 2, -2. There's no dark fringe at the center, so we don't have a zero dark fringe. It's just terminology, it's not going to be that important. But this is what we call dark fringes and bright fringes. Okay? Any other question? All right. So back to the water wave. So why do I say this is a wave pattern? When you have a laser shining at a double slit, it creates two wave sources, just like these two balls on the surface of the water. Electromagnetic wave doesn't need to travel on water. It can propagate in vacuum, but it's still wave, so you can understand its behavior by looking at water wave. You see, the interference of these 2 point source is to create these lines which the wave is always having destructive interference. So when you put a screen which allows you to see the light, you can see the intensity goes down, up, down, up, down, up, and that's the diffraction pattern. That's the interference pattern you see. In the middle, there is light propagating, but you cannot see the light unless it enters your eyes. So you have to put a screen there. The light hit the screen, got spread out in all directions, and one of them hit your eye, and you see that some spots have more light coming out, and some have fewer. Those knots with destructive interference is those blurry lines on the entire 2D wave pattern. And if you move the screen closer, you can see following this line, the bright fringes and dark fringes should become closer because you just follow this blurry line, and the closer you are to the double slit, the closer the separation, the dark fringe and bright fringes. Yeah.
Shouldn't the crest of the middle one be higher than the others?
So if you just look at experiment, the intensity is not that different. It will be very different for a single slit. For a single slit, the center bright fringe is a lot brighter than the other part, but for double slit, the intensity dies out in a slower manner. You will first hit another bright fringe first before it dies out significantly. It's because it takes very few. It has something to do with how the waves are canceling each other. So when you go from no, you do not see that. You do not see it. Okay. So when you go from the first bright fringe to the second bright fringe, you are just changing the distance to the source by a wavelength, which is nanometer. Compared to the distance of the screen, it's not that much. But when you have single slits, the way they cancel each other is more complicated, which I do not plan to tell you until final. So
I'll just Google it.
You can Google it or look at the textbook. Okay. Any other question? Good. Good. So another hint: if you are farther away from the screen, the gap between the fringes should spread out. If you're closer, the pattern will be closer. So that's why I put this double slit so far away from your screen, because that's how I make the pattern big enough for the whole class to see. Same thing for your experiment. When you're doing experiment, you will do this double slit. Make sure you put your laser far away from the wall so you have a long distance to measure the separation between the dark fringes. All right. Question time. You do not know the answer because I do not show them by accident. Which one should be caused by the red laser? So there are different colors of laser, but I just make the photo black and white. What you know is that different color have different wavelengths. These are all the same double slit, but the laser have different color, different wavelengths. So I think it's obvious that the bottom one is wider, the top one is smaller. Which one is caused by the red light, which have the longest wavelength in visible light? $20. I guess 47 is the people we have here. Oh, good. We know that it must be either A or C because I'm looking at red, which is like the extreme value. So it's either the shortest or the longest. Good, good, good. So remember, when you have longer wavelengths, you have more diffraction. It goes opposite. Smaller, does it go opposite? No. So smaller opening, more diffraction. Longer wavelengths, more diffraction. So we know diffraction will allow the wave to spread out, and therefore the longer wavelengths spread out more on the interference pattern. But we can have a more quantitative way to understand it. So remember, when you go from the center bright fringe, which is always bright, no matter what wavelengths you use, the center is always equally far from the two slits, so it's always a bright fringe. And when you move away to the side, you want to move enough such that the path difference equals half the wavelength. So if you increase the wavelength of the laser, you need to move further away to the side to reach this criteria. This delta L is just geometry. It doesn't change it doesn't matter which color you use, this geometry is always the same. So if you have a longer wavelength, you need to shift to the side more for this path difference to reach half of your wavelength. So if you have longer wavelengths, you have to move more, and on your diffraction pattern, on your interference pattern, you should see the dark fringe at a wider position. So that's why you see for longer wavelengths, you have to move more to the side to hit the dark fringe, and same with everything else. So you know for longer wavelengths, the pattern just becomes more easier and more widespread. Any question? All right, let's add more fringes. So again, now we are going to look at diffraction grating, which is a lot of slits. What we see already is that adding a lot of slits allows you to concentrate the energy at some spots. How does that happen? As an example, I'm just going to show you the scenario which you have 4 slits. So at the center, even though you say this one's farther, this one's closer, but if I move the screen further enough, then these two will be equally far at this point. These two will be equally far at this point. So together, they are all helping each other. They have constructed interference. So you know at the center is still a peak. And what happened at the side is that they still form constructed interference by hitting the 1 lambda criteria. So they are all, the paths between these slits to the point on the screen all differ by 1 wavelength. So if you have 1 wavelength of difference, they have constructed interference, and they all sum up to a high peak over there. But what happens in between? If you have multiple slits, you can have different kind of combinations. You can have scenario which 1-3 cancels by pair, and 2-4 form a pair and cancel each other. There are more options. Instead of 1-3, 2-4, you can form 1-2 as a pair, and let 1 and 2 cancel, and switch 4 cancel. So these different dark spots between the two high peaks correspond to different combinations of these slits. If you have a lot of slits, then you can have a lot of different ways to pair them up and cancel each other. So when you move from 0 lambda to 1 lambda of path difference, you will pass through a whole bunch of points which they pair up in different ways and cancel each other. So that will suppress the energy between the two bright peaks. But we say energy is conserved. So if you have so many destructive interference between the two constructive interference, those energy must go somewhere. So they must go into the high peaks and get concentrated. So that's why for diffraction grading, you can concentrate the energy at the high peaks. So far, so good? Now, so this is on your textbook. This is just double slit interference. This is 3 slits, but all the slits are equally wide, spread out. So the gap or the distance between 2 slits is always the same. You just keep adding more slits without changing the separation between 2 slits. What you see is that if you have 2 slits, it's just double slit interference. Then you have this peak pattern. 3 slits give you more ways to cancel. So between the two high peaks, you will have more knots, and that decreases the energy at this part, and those energy must go into the constructed interference peak. If you have 4 slits, then you have more different combination to cancel between the two peaks, and those energy again must be conserved and got concentrated to the bright peak. So as you add more and more slits, you just get sharper and sharper at the constructed interference peaks. Okay? Note that if you maintain the displacement between every 2 slits, then the location of these bright peaks will always be the same. If you add more slits, you just keep growing higher and higher, but the location of the peaks will not change. They just become sharper and brighter. Okay? All right. So, which one is a single slit? Oh, we have so many more people now. Okay. Well, if you still have technical issue with the eye clicker, just take a selfie and send it to me. For today and last week, I will just give you full credit for 1 picture, but after that, you need to take selfie for every single problem that you miss for technical issue. All right. I hope I have a nice, good. So the biggest difference between single slit and the other pattern is that the center bright spot is wider compared to the other white spot. Not compared to the other device. you see, for double slit, every single bright spot is pretty much equally wide. Same with the diffraction gradient. They are equally widespread, but for the single slit diffraction, the center one is actually twice as wide compared to the rest. And that is just something I want you to keep in mind. We will prove that after the midterm. Okay? Any question? All right, so the last thing we want to look at is what if instead of a slit, I have a inverse slit, which instead of having opening and blocking everything else, I have a wide open space, but I only block the part that corresponds to the width of the slit on the top. So what you will see is that you create pretty much the same pattern. Having a single slit and an inverse slit end up being the same in the interference pattern that created. Not exactly the same. You will see that for the inverse slit, the center will be darker compared to the slit itself. But if you just want the pattern caused by this interference, this saves a lot of money. This technique is used in the antenna design if you want to save a lot of cost by creating just an inverse slit instead of a huge material, a huge wall. You can use this principle called Babinet's principle. You will use this principle to measure the width of your hair in one of your experiments. So you will analyze the result with single slit interference pattern, even though your hair is not a single slit, it's a inverse single slit. So we know if we only have the laser itself, that is what we see. We see the intensity is like a block function. But what I'm plotting right here is not the intensity. I'm trying to plot the wave itself, so the wave can oscillate up and down. When you have a single slit and you know it corresponds to that intensity, it means the wave must go up and down at the side, not just at the middle. Here, only the middle part can go up and down. Only the middle part has non-zero amplitude. But when you have a single slit, the outer part also have non-zero amplitude. And because I'm plotting a wave, the wave can go negative. And if I have time to create an animation, you will see the whole thing flipping up and down, up and down. And the center part will have bigger amplitude because you know the intensity is bigger. This part is like a knot, which will not have any intensity. And this part will also oscillate with some intensity, but smaller compared to the center right fringe. Now, we know wave satisfies superposition. The entire laser consists of this part and the part outside. So if the entire laser will create this wave, then it means the wave created by the center part and the outer part should sum up to this wave. So instead of addition, now you're doing subtraction. You want this plus something and equals this wave. So you know if you want the outside part to cancel, then the wave created by the outside part of the laser must be equally large, but in the opposite phase, the opposite direction, compared to the wave created by the center part of the laser. So the outside part should cancel, but for the center peak, it should not exactly cancel because they should add up to a spot at the center. So you know the wave created by all the laser that pass through the inverse slit should create a pattern that is opposite to the pattern created by a single slit, but the center will not cancel exactly. Okay? So that's why they will have the same interference pattern. Okay? The dark fringe will have the location of the dark fringe will be exactly the same because you need 0 plus 0 to equal 0. So you can use the formula for the dark fringe location to measure the width of your hair, even your hair is not a single slit. Yeah?
If we took the single slit and we made sure it was not centered, we put like uncentered, would it like cause a difference?
Good question. Well, I will say because the pattern of the single slit is still the same. So indeed, if you look at not the exterior part, but just the right-hand side, they should create the same pattern. It sounds amazing or unrealistic, but if you look at the math, A plus B equals C, then that must be the result. And you know math will work in this class because this is a physics class. Any other question? All right, so that's all I have to say for this lecture. There will be more on Thursday and a discussion.